8.3, separable differential equations. So I have here at the top of the page, g of y times dy dt. So it could be some kind of um, differential equation, and it equals h of t. So what it means by separable is the dy dt are almost like independent of each other. If I multiply both sides by dt, I can then say I'm separating my variables, so I only have the terms of y on the left-hand side and in terms of t on the right-hand side. So I've separated the variables in this differential equation. I've grouped them. Variables on y on one side, variable of t on the other side. So this then is, if I wanted to find a solution to it, this becomes where I can take the antiderivative or the integration of each side to find a solution for this separable differential equation. The problem is not every equations that were given can be separated. So I have here, for examples, A. Remember, we want to separate y onto the other side. And notice when I did up here, I had g of y times dy. Remember, that would be like height times width kind of situation if I was trying to find something in that terms. But if it was this one, I'm going to go ahead and try to separate the variables. I would subtract y from both sides. And I've got this, but then if I went to go multiply both sides by the dt, I am not separating it completely because I would have this. So in this case, this one I cannot manipulate in order to separate the variables. This one is not separable. If we look at B, I see something kind of messy too, but let's see if we can try to still separate it. So for here, I'm going to go ahead and I'm going to multiply dt to both sides. Okay. I need to go ahead and just get that y variable over. So if I divided both sides by a y, I would get dy over y equals, and then this then is in a sense, I'm multiplying these and these reduce. And then in this case, I can see that I definitely have separated the variables. I have y, dy on one side and t, dt's on the other side. So this one is separable. And if I look at C, we just have to remember that all we have to do, if you're given this equation, you can separate this. This would equal e to the x times e to the y. Remember, when you multiply like bases, you're really adding the exponents. And if that's the case, this is definitely would be separable in this case. So this one also is a yes. So we have here then our box of information for solving separable equations. We have that in practice, the following steps are used for first order separable differential equations. So we're talking about first order equations only in this case. We separate the variables to get the y on one side or the t on the other side. We can find the antiderivative. Both integrations produce an arbitrary constant of integration that may be combined into one arbitrary constant. If initial condition is given, we can evaluate it. So this is what number 3 means. Number 3 says, if I can have one, I could take the antiderivative of the left-hand side. And normally, since it's indefinite, we would say plus c, and I'll call it c plus 1, or c sub 1. And in the right-hand side, if I take the antiderivative, we would do an arbitrary constant. In this case, I could subtract this c over here and get this result. Remember, since it's just a constant, if I'm adding or subtracting two constants together, I can say, well, it could be this. It's still just another constant. So when we talk about both producing arbitrary constants, but may can be combined into one. So when we're talking about this, we're going to really just go ahead and give our antiderivatives in this form, with only the plus c on the right-hand side, so that then we could do step 4. If an initial condition is given, we can find that constant. So let's go ahead and do a couple of examples. Number 5. Number 5 gives us this function, and they want us to go ahead and try to separate it and find the antiderivative of it. So I'm going to go ahead and I'm going to go and I'm going to multiply both sides by dt first. Let's do that. And then from here, I'm going to go ahead and divide both sides by t to the negative 3. And then I'm going to go ahead and neaten this up by moving the exponent up so I get a positive exponent. And now I have it where a nice way I can take the antiderivative of both sides. And I get y is equal to t to the 4th over 4 plus c. Let's do another one. If I want to go ahead, let's do number 7. Given this function, let's go ahead and separate and find its antiderivative or solution. So I'm going to go ahead and multiply both sides by y and multiply both sides by dt. And I would get this. And then I'm going to go ahead and take the antiderivative of both sides. So notice then that I get an equation that I have a y squared divided by 2 on the left-hand side. I want to go ahead and solve for y in this case. So I'm going to go ahead and multiply both sides by 2. And I'm going to still call it c because I'm just multiplying it by 2. So I'm just going to leave it as c. It's still some arbitrary constant. And then I want to go ahead, I'm still trying to solve for y, so I'm going to take the square root of both sides, and I get a positive and negative square root of 2t cubed plus some constant. So this would be my answer for number 7. Now let's try one that has an initial condition. We're going to do number 21. So I'm given this function and this initial condition. And we want to go ahead and separate and take the antiderivative and evaluate for the arbitrary constant. So I'm going to go ahead in this case, I'm going to multiply both sides by dt. So let's see, if I expand this out, I get if I divide both sides by y, wait a minute. I still didn't separate y's. If this is the case, then if I cannot manipulate this, I'm going to go ahead and say this is not separable. And that's all I can say with this one. I cannot go ahead and do any more work. It was not separable. So let's go ahead and try one more that we know we have a constant in. So let's do 27. Given this function, we can separate this one. I'm going to multiply both sides by y, and I'm going to, multiply both sides by dt. So I have this, and I'm going to take the antiderivative And I'm going to have, oops, let me go back and write down the initial condition we have. And then we're going to go ahead and take the antiderivative of this. And then I'm going to go ahead and find my initial condition. So I'm going to plug in for uh, 2 for y. I can go ahead and actually speak here. And 1 for t. So I'm plugging in. And I want to go ahead and try to solve this for c. So when I go ahead and solve this for c, I do get c equals 3/2. So if I go ahead and plug this back in, I'm going to try to solve for y. So I'm taking this equation. And I'm going to multiply both sides by 2. I need to solve for y still. So I'm multiplying everything through by 2. And then I'm going to be taking the square root of both sides. All right. So this is one way of doing this one. Another way of doing this one, if depending on what the problem wanted, I could have gotten it into, in order to be able to try to graph it, I could have taken this equation and seen, oops, if I would have to subtract the t squared. This might be becomes maybe hyperbola that we can graph. It just becomes an easier way of graphing it if we have to. This one does graph like this. I think I drew that right. So this would be all I need to go ahead and say on this one. But I want to add into this video the ones that we're going to not have on our Math Excel homework, but I'm going to give you out of the textbook. It's Newton's law of cooling. And we're given this equation here. And sometimes, though, we may see this rewritten as CE to negative KT plus A. This equation here, that part of it in the parentheses, is our C. So what we want to do when talking about Newton's law of cooling, we usually have A, which is the ambient temperature or the room temperature or surrounding temperature or whatever you want to call it. They call it A for ambient temperature. And then we also want to have T naught, which is your initial temp of the item, whatever it may be. And then we're going to have T, which is a final temperature, if I can spell it, of item. And then we want to have the K, which is the rate of cooling. And T, little t, is time. How long is it taking to get there? So I want to go ahead and just try one example, and then you can do a couple of the homework problems from the textbook. So what we have here is we're going to say a bowl was removed from a pottery kiln. And when it was removed, the item was 200 degrees Celsius at removal. And then it's placed on a rack in a room with an ambient temperature of 20 degrees Celsius. So our ambient temperature, our T naught, and then it says 2 minutes after it was taken out of the kiln and sat resting for 2 minutes, the temperature of the bowl was 160 degrees Celsius. So now they're saying, okay, given all this information, you're going to need to find your K and give a general cooling formula for this item. And we're going to use, remember, we're going to start with first this equation. and we need to find K, and that's my answer is going to look like that. So we want to go ahead and plug and chug is really what it comes down to. So in here, if we want to find this C, we know it's T naught minus A. So this is, our C in that case is going to be 180 degrees Celsius, and we're going to have e to the negative, and now I'm going to use this info to find my k. So I'm going to go ahead and say the negative k, and our time is going to be 2 minutes, and we had an ambient temperature of 20 degrees, and when this was to here, T of 2 is 160 degrees Celsius. So I'm going to go ahead and replace that. So I'm given this equation, and I need to solve for K. So it becomes basic algebra. At that point, we're going to subtract we're going to 20 degrees and get 140. And then we're going to divide by the 180. I'm going to write it as that right now. And we're going to say 140 divided by 180. We're going to leave it in fraction form. And then in this case, I take the natural log of both sides. And if I take the natural log of both sides, I get this equation. And then I want to go ahead and divide by the negative 2. And this would be my K. If I want to go ahead and find a decimal form of it, it's approximately 0.126. I'm going to use that. So my equation that they want at the end should be approximately, because we're not 100% sure with this rounding of K, is 180 degrees Celsius times e to the negative 0.126 T. And this would be my answer for Newton's law of cooling. So this one, it's not anything difficult, but it's just a little bit plug and chug and remembering taking the natural log of both sides to solve for an unknown exponent.